There's a line in space nobody talks about. Cross it, and you can never go back. Not to Earth, not to your family, not even to your own timeline. Anyone who leaves for the stars is already dead to everyone they've ever loved, and it has nothing to do with distance. If you want to understand your place in this vast universe, hit that subscribe button. Now let's get started. Let's say humanity develops propulsion technology capable of reaching 10% the speed of light. That's roughly 30,000 kilometers per second, a velocity that would require energy expenditures beyond anything we currently possess. At 10% light speed, the journey to Proxima Centauri would take about 43 years. Add in acceleration and deceleration time, and you're looking at a human lifetime spent in transit. Here's the first hint of why return becomes impossible. Fuel. Every kilogram of mass you accelerate to relativistic speeds, speeds approaching the speed of light, requires enormous amounts of energy. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, tells us that the mass of fuel needed grows exponentially with the change in velocity you're trying to achieve. To accelerate a spacecraft to even a modest fraction of light speed requires carrying fuel that itself has mass, which requires more fuel to accelerate, which requires even more fuel, creating a vicious cycle. Current concepts for interstellar propulsion attempt to work around this problem. The breakthrough Starshot initiative, announced in 2016, proposes sending tiny spacecraft weighing just a few grams to Alpha Centauri. These miniature probes would be accelerated by powerful Earth-based lasers pushing against ultra-thin light sails. The idea is to reach 20% the speed of light, allowing the probes to reach Alpha Centauri in roughly 20 years. But here's the critical detail. These are one-way missions. There's no mechanism for slowing down, no method for return. The probes will simply fly past their target, snap some pictures, and continue into the void forever. Why can't they turn around? Because turning around requires the same amount of energy you used to speed up in the first place. If you spent decades accelerating to relativistic speeds, you'd need to spend decades decelerating, then accelerating again in the opposite direction, then decelerating once more when you arrive back home. The fuel requirements become absurd, requiring you to carry fuel to slow down, fuel to speed back up, fuel to slow down again, and fuel to carry all that fuel. The mathematics simply don't work with any known physics. Some have proposed generation ships, massive vessels that sustain human populations across multiple generations during the centuries-long journey to nearby stars. I've actually explored the immense challenges of this concept in detail in my video, Why Generation Ships Are a Terrible Idea, where I break down the biological, psychological, and engineering nightmares that make these vessels nearly impossible with our current understanding. The fundamental problem remains, even if you could build a self-sustaining ark in space, the return journey multiplies every challenge you faced going out. It's on the card above and pinned on the comments, but fuel isn't even the biggest problem. The true barrier to return is something far more strange, far more fundamental to the fabric of reality itself. It's a phenomenon predicted by Albert Einstein over a century ago, confirmed by countless experiments, and operating all around us every moment of every day. It's called time dilation, and it means that time itself flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. Einstein's special theory of relativity, published in 1905, revealed something profound about the universe. Time is not absolute. The rate at which time passes depends on your frame of reference. For objects moving slowly compared to the speed of light, the effect is negligible, but as you approach relativistic speeds, time dilation becomes dramatic, profound, and utterly unavoidable. The mathematics is elegant and terrifying. The time dilation factor is calculated using the Lorentz factor. named after Dutch physicist Hendrik Lorentz. The formula shows that as your velocity approaches the speed of light, time for you, the traveler, slows down relative to everyone back home. At 10% light speed, time dilation is barely noticeable, just 0.5% slower. At 50% light speed, time slows by about 13%. But at 90% light speed, time for you moves at less than half the rate of time back on Earth. Let's run through a thought experiment. Imagine you board a spacecraft capable of sustained acceleration at 1 Earth gravity, 1g. This would feel comfortable, like standing on Earth's surface. You accelerate continuously for the first half of your journey, reaching incredible speeds, then flip the ship and decelerate for the second half. Your destination, a star system 40 light-years away. From Earth's perspective, this journey takes slightly more than 40 years at minimum, plus acceleration and deceleration time, roughly 45 years total. But on your ship, due to time dilation, only about 12 years pass. You arrive at your destination having aged 12 years, while 45 years have elapsed on Earth. Now you want to come home. You execute the same journey in reverse. Accelerate, cruise, decelerate. Another 12 years pass for you. Another 45 years pass on Earth. You step off your spacecraft having aged 24 years since departure and discover that 90 years have passed on Earth. Everyone you knew is elderly or dead. The world has moved on. Technology has advanced. Culture has shifted. You are, in essence, a time traveler who has journeyed 90 years into Earth's future. This is the gentler version of the problem. Now let's accelerate faster, push harder toward the ultimate speed limit. Imagine a spacecraft capable of reaching 99% the speed of light. At this velocity, time dilation becomes extreme. The Lorentz factor jumps to about 7.1. A journey that takes 100 years from Earth's perspective takes only about 14 years for you. Round trip, 200 years on Earth, 28 years for you. Everyone and everything you knew is 2 centuries gone, but it gets stranger, much stranger, because the closer you get to light speed, the more dramatic this effect becomes. At 99.9% light speed, the Lorentz factor is around 22. A trip that takes 1,000 years from Earth's viewpoint takes you just 45 years. At 99.99% light speed, we're talking about a factor of 70. 10,000 years on Earth, 140 years for you. You could, in principle, travel to the other side of the galaxy 50,000 light-years away and experience the journey as taking only about 700 years at 99.99% light speed, while 50,000 years pass on Earth. Let that truly sink in. If you left today and traveled to the galactic center and back at near light speeds, you could theoretically survive the journey personally, but you would return to an Earth 50,000 or more years in the future. Human civilization as we know it would be unrecognizable, possibly extinct. Languages, nations, even continents would have changed. You would be more alien to future Earth than a Neanderthal appearing in our world today. This is not science fiction. This is established physics, confirmed by thousands of experiments. Particle accelerators observe time dilation constantly. Muons, subatomic particles created when cosmic rays strike our atmosphere, should decay in microseconds, but when they're created moving at near light speeds, they last much longer from our reference frame, allowing them to reach Earth's surface before decaying. The only explanation is time dilation. GPS satellites orbiting Earth must constantly adjust their clocks to account for both gravitational and velocity-based time dilation. Without these corrections, GPS would drift by kilometers per day. The famous twin paradox, first proposed in Einstein's era, illustrates this perfectly. One twin stays on Earth. The other travels to a distant star at relativistic speed and returns. The traveling twin is younger, sometimes dramatically so. This is not a paradox at all, it's reality. Soviet cosmonaut Sergei Krikalev spent 803 days in orbit aboard the Mir space station, an international space station. Due to his high orbital velocity, he experienced time dilation of roughly 0.02 seconds. He aged 0.02 seconds less than someone on Earth's surface. It's a tiny effect at orbital speeds, but it's measurable, real and confirmed. Now, scale that up to interstellar velocities and the effect becomes life-altering, civilization-altering. You cannot return to your own time. Physics forbids it. You can only return to Earth's future. But time dilation, as profound as it is, represents only one barrier to return. There's something even more dangerous lurking in the void between stars, something that could kill you long before time dilation becomes your primary concern. I'm talking about the interstellar medium itself. Space, as we often hear, is not truly empty. Between the stars lies a thin soup of matter, primarily hydrogen and helium atoms left over from the Big Bang, enriched over billions of years, with heavier elements forged in stellar furnaces and scattered by supernovae. On average, interstellar space contains roughly 1.8 hydrogen atoms per cubic centimeter. That might sound like nothing. In a terrestrial laboratory, we'd call that an excellent vacuum, but when you're moving at relativistic speeds, that thin gas becomes a weapon. Here's why: velocity transforms perception. When you're stationary, a hydrogen atom drifting through space is harmless, but accelerate to a significant fraction of light speed, and suddenly that same atom is coming at you with enormous kinetic energy. At 10% light speed, each hydrogen atom strikes your ship with the energy of a particle in a medical X-ray machine. At 50% light speed, those atoms carry energies comparable to particles in a radiation therapy beam. At 90% light speed and beyond, every single hydrogen atom becomes a cosmic ray, a high-energy particle capable of tearing through matter, ionizing atoms, breaking molecular bonds, and shredding DNA. Research published in scientific journals has calculated the radiation dose received by spacecraft at various relativistic speeds. The findings are sobering. At around half the speed of light, interstellar hydrogen begins delivering radiation doses that would be lethal to humans within hours or days without extraordinary shielding. At higher speeds, the effect intensifies exponentially. A paper titled "Speed Kills: Highly Relativistic Spaceflight Would Be Fatal for Passengers and Instruments," published in the journal Natural Science in 2012 by William and Amanda Edelstein, laid out the mathematics in stark detail. At velocities approaching light speed, the thin hydrogen medium transforms into intense radiation. The dose rate scales with velocity. At around 90% light speed, the radiation flux becomes so intense that even thick shielding cannot fully protect biological organisms or sensitive electronics. The problem is fundamental. You cannot simply add more shielding because shielding has mass, and mass requires energy to accelerate. Every kilogram of shielding multiplies your fuel requirements. There's a point where the shield becomes so heavy that you cannot reach relativistic speeds at all. It's a vicious engineering trap with no clear solution using known physics. But wait, it gets worse. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, pervade the galaxy. Even at rest, astronauts beyond Earth's protective magnetic field experience increased radiation exposure. The Apollo astronauts reported seeing flashes of light with their eyes closed. These were cosmic rays passing through their eyeballs and optic nerves, creating brief signals. On the International Space Station, shielded by Earth's magnetic field, astronauts receive roughly 50 to 200 millisieverts of radiation per year, compared to about 3 millisieverts per year on Earth's surface. Venture beyond the magnetic shield, and cosmic ray exposure increases. Travel to Mars, and astronauts would receive radiation doses of around 300 millisieverts during a 6-month journey each way. That's manageable, though not without risk. But now accelerate to relativistic speeds. Cosmic rays, which are already energetic, become even more dangerous. Due to relativistic beaming, the cosmic ray flux appears to increase and concentrate in the forward direction of your motion. Particles that were spread across the sky now seem to come predominantly from ahead. Their energy, as measured in your reference frame, skyrockets. A 2026 review in the European Physical Journal titled Radiation Risk Mitigation in Human Space Exploration emphasizes that radiation remains the #1 risk to human health beyond low Earth orbit. The paper discusses how cosmic rays damage DNA, increase cancer risk, harm the cardiovascular system, and impair the central nervous system. Neurons do not regenerate easily, meaning radiation damage to the brain can be permanent. Cognitive decline, memory loss, and behavioral changes have been observed in animal studies exposed to simulated cosmic rays. Now imagine enduring this for decades during an interstellar journey, with the added complication of time dilation, meaning that while you experience a few years or decades, Earth-based mission control experiences far longer. Communication becomes increasingly delayed and eventually meaningless. Then there's another insidious problem: material degradation. A spacecraft are made of metals, composites, electronics, polymers. Radiation damages all of these. High-energy particles displace atoms in crystal lattices, creating defects that weaken materials. Over time, structural components become brittle. Electronics malfunction as transistors are struck by ionizing particles. Memory chips experience bit flips, solar panels degrade. Every system slowly breaks down under the relentless bombardment. A 2021 study published in the Astrophysical Journal examined the damage to relativistic interstellar spacecraft caused by impacts with interstellar gas. The study, focusing on the breakthrough Starshot concept, calculated that at 20% light speed, hydrogen and helium atoms implant themselves into the spacecraft's forward surface. Over time, these implanted atoms form bubbles in the material, causing blistering and exfoliation. Essentially, the surface layer peels away like sunburned skin. For a journey lasting even 20 years, material erosion could become catastrophic, and this brings us back to the impossibility of return. Even if you somehow survive the outbound journey, protected by advanced shielding and medical countermeasures we have not yet invented, turning around means facing the same gauntlet again: the radiation, the material degradation, the time dilation. Double the exposure, double the risk, double the time lost. But perhaps the most philosophically devastating barrier to return isn't technological at all, it's cosmological. It's built into the very structure of space-time itself. I'm talking about the expansion of the universe, and specifically the accelerating expansion driven by dark energy. In 1998, 2 independent research teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rias, made a discovery that shocked the scientific world. They were studying Type Ia supernovae, stellar explosions that shine with predictable brightness. By measuring how dim these supernovae appeared compared to their known intrinsic luminosity, astronomers could calculate their distance. By measuring their redshift, they could determine how fast they were receding due to cosmic expansion. The expectation was simple: gravity should slow the expansion. The universe should be decelerating. Instead, the data showed the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than predicted. The universe wasn't just expanding, it was accelerating. The rate of expansion was increasing over time. This discovery earned Perlmutter, Schmidt, and Rias the Nobel Prize in Physics in 2011. It fundamentally changed our understanding of the cosmos. To explain the acceleration, physicists invoked something called dark energy, a mysterious form of energy that permeates all of space and exerts a kind of repulsive gravitational effect. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter, the invisible stuff that holds galaxies together, accounts for about 27%. Ordinary matter, everything we can see, stars, planets, gas, dust, makes up less than 5%. Dark energy is modeled mathematically as a cosmological constant, symbolized by the Greek letter lambda. Albert Einstein originally introduced this constant in 1917 to keep his model of the universe static, balancing the attractive pull of gravity. When cosmic expansion was discovered, Einstein reportedly called the cosmological constant his greatest blunder, but the late 1990s brought it roaring back. The cosmological constant, it turns out, wasn't a blunder. It's a fundamental property of the universe. The lambda CDM model, lambda standing for the cosmological constant and CDM for cold dark matter, is now the standard model of cosmology. It describes a universe that began in a hot, dense state 13.8 billion years ago, expanded and cooled, formed structures under gravity, and now finds itself in an era dominated by dark energy, accelerating outward faster and faster. Here's where this becomes relevant to interstellar return journeys. The accelerating expansion means that distant regions of space are receding from us at ever-increasing speeds. There exists a boundary called the cosmic event horizon, beyond which objects are receding so fast that light they emit today will never reach us, no matter how long we wait. This horizon currently sits at a distance of roughly 16 billion light-years in comoving coordinates. Now, comoving coordinates can be confusing. They're a way of measuring distance that accounts for the expansion of space itself. Think of the universe as a balloon, with dots on it representing galaxies. As the balloon inflates, the dots move apart. The distance between dots increases, but each dot stays at the same position on the balloon's surface. Comoving distance is like the position on the balloon, while proper distance, the actual physical separation at any given moment, increases with expansion. In proper distance terms, accounting for expansion, the edge of the observable universe is about 46 billion light-years away, even though the universe is only 13.8 billion years old. Light from those distant regions has been traveling toward us for nearly the entire age of the universe, but during that time, space itself has been expanding, stretching the distance. The cosmic event horizon is different from the observable universe. The observable universe is bounded by the particle horizon, the maximum distance light could have traveled to reach us since the Big Bang. The event horizon marks the boundary beyond which light emitted now will never reach us in the future, no matter how long we wait. Because space is expanding too fast, objects beyond the event horizon are forever beyond our reach. We can observe some of them now because they emitted light in the distant past when they were closer and not yet beyond the horizon. But any light they emit from this moment forward will never arrive. They are causally disconnected from our future. We will never affect them. They will never affect us. And this brings us to the crux of the problem for interstellar travelers. If you travel far enough, fast enough, for long enough, you could cross beyond Earth's cosmic event horizon. At that point, no signal you send, no matter how powerful, will ever reach Earth again. Even traveling at the speed of light, your messages will be swept away by the expansion of space, forever redshifted, forever retreating, never arriving. Research published in Arxiv, a preprint repository for scientific papers, explores these cosmological horizons in detail. A paper by Tamara Davis and Charles Leanweaver titled Expanding Confusion: Common Misconceptions of Cosmological Horizons and the Superluminal Expansion of the Universe, clarifies that galaxies we currently observe often have, and always have had, recession velocities greater than the speed of light. This doesn't violate special relativity because it's not motion through space, but rather the expansion of space itself carrying them away. We can observe these superluminal galaxies because the light they emitted long ago, when they were closer, has had time to traverse the expanding space. But eventually, as we look to more distant and ancient galaxies, we approach the edge of the particle horizon, beyond which no light has had time to reach us yet. And looking forward in time, the event horizon defines a boundary beyond which no future light will ever reach us. For an interstellar traveler, this has profound implications. Imagine you journey to a galaxy far enough away that during your voyage, the accelerating expansion of the universe pushes that galaxy beyond Earth's future event horizon. You arrive, look back, and realize you can still see Earth, faintly distantly. You send a message home, but that message, even traveling at light speed, will never arrive. Space is expanding too fast. The photons you send will redshift endlessly, their energy draining away, asymptotically approaching zero, never reaching their destination. You cannot return, not because the journey is too long or too dangerous, though it is both, but because the universe itself has moved on. The destination you left is now unreachable, even in principle, by any signal or object traveling at or below light speed. You are stranded not just in space, but in a causally disconnected region of space-time. Now, let's add another layer of complexity: the Hubble sphere. The Hubble sphere is the distance at which the recession velocity of space equals the speed of light. Due to the accelerating expansion, the Hubble sphere is currently larger than the event horizon and will continue to grow, but at a decelerating rate. Galaxies just beyond the Hubble sphere are receding faster than light, yet we can still see some of them, as mentioned earlier, because their light was emitted when they were within the Hubble sphere. But here's the key point: if you travel to a location beyond the current Hubble sphere and then try to send a signal home, that signal must first overcome the expansion of space just to make any headway toward Earth. Depending on the specifics of the universe's expansion rate and your distance, your signal might eventually make it, or it might not. The boundary between these possibilities is the event horizon. A 2026 paper published in the journal Arxiv, titled The Edges of Our Universe by philosopher and cosmologist Toby Ord, explores these causal limits in detail. Ord distinguishes between the affectable universe, the regions we can influence by sending signals or traveling, the observable universe, what we can currently see, the eventually observable universe, what we will be able to see in the future if we wait long enough, and the ultimately observable universe, the maximum extent of what could ever be observed under ideal conditions. For a civilization planning interstellar voyages, these boundaries matter immensely. The affectable universe defines the maximum reach of any signal or spacecraft we send. Due to the accelerating expansion driven by dark energy, the affectable universe is actually smaller than the currently observable universe. There are galaxies we can see today that we can no longer reach, even if we left right now at the speed of light, because space is expanding too fast. This means that the number of galaxies humanity could ever potentially visit or contact is finite and shrinking. Every moment we wait, more galaxies slip beyond the cosmic event horizon, forever out of reach. In a very real sense, the universe is closing its doors on us, one galaxy at a time. Now imagine you're an astronaut who left Earth decades or centuries ago, from Earth's perspective, to explore one of these distant galaxies. During your journey, that galaxy and you along with it crossed beyond the event horizon. You're alive, you're conscious, you're exploring. But from Earth's perspective, you've vanished into an inaccessible region of space-time. No message you send will ever return. No trace of your discoveries will ever reach home. You are lost, not to death, but to cosmology. And here's the emotional weight of it. You might not even realize it immediately. You could arrive at your destination, settle on a planet, build a new life, and only gradually, over years or decades, come to understand that the silence from Earth isn't due to technical failure or time dilation, but because you've crossed a one-way boundary in space-time itself. You can still see Earth, or at least the ancient light from Earth, but Earth can no longer see you. You're a ghost in the cosmic machine, visible to yourself but invisible to home. This isn't merely theoretical anxiety. It speaks to something profound about the human condition. We are social beings, evolved over millions of years to live in communities, to communicate, to share experiences. Isolation is one of the most severe psychological stressors known to our species. Studies of Antarctic winter over crews, submarine sailors, and astronauts on the International Space Station consistently document psychological challenges, depression, anxiety, interpersonal conflict, cognitive decline, sleep disturbances, and what researchers call the third quarter phenomenon, a period roughly 3 quarters through a long mission where morale plummets and psychological symptoms peak. A landmark study published in PLOS One in 2014 examined the Mars 500 simulation, where 6 men were confined in a 550 cubic meter chamber for 520 days, simulating a journey to Mars and back. Researchers observed substantial individual differences in response to isolation and confinement. One crew member showed symptoms of depression in 93% of mission weeks. Conflicts with mission control were reported 5 times more often than conflicts among crew members. Sleep disturbances, chronic fatigue, and attention deficits plagued several participants, and that was a simulation on Earth, where participants knew they could technically leave in an emergency, where the psychological safety net of home was always present, even if unused. Now imagine true interstellar travel, where there is no emergency exit, where Earth recedes into the darkness and becomes first a pale blue dot, then a faint star, then nothing distinguishable from the thousands of other stars in the sky. The psychological toll would be immense. A 2023 review published in the journal Translational Psychiatry, titled Long-Term Spaceflight Composite Stress Induces Depression and Cognitive Impairment in Astronauts, explores how the unique environment of space, a composite of microgravity, isolation, confinement, noise, circadian rhythm disturbance, and radiation exposure, affects the brain. The paper describes neuroplastic changes, alterations in how the brain's neural networks form and reorganize that could lead to depression, anxiety, and cognitive impairment. Neuroplasticity is normally beneficial, allowing the brain to adapt to new environments. But the extreme stresses of spaceflight can induce maladaptive neuroplasticity, where the brain changes in ways that impair function rather than enhance it. Studies on astronauts returning from the International Space Station have documented structural brain changes, including shifts in cerebrospinal fluid distribution, expansion of the brain's ventricles, and alterations in white matter connectivity. Some of these changes persist months after returning to Earth. Now extend these findings to interstellar missions lasting not months, but years, decades, or even generations. The psychological and neurological toll could be catastrophic. And here's the cruel irony. Even if you develop depression, cognitive impairment, or other mental health issues during the voyage, you cannot turn back. The physics and cosmology we've discussed ensure that. You must continue forward into an uncertain future with a degrading mental state in a fragile spacecraft hurtling through the void. But the human mind isn't the only system degrading during such a journey. The human body, exquisitely adapted to Earth's one-gravity environment over millions of years of evolution, begins to break down in the microgravity or low-gravity environments of space. On the International Space Station, Astronauts experience bone loss at a rate of 1 to 2% per month in weight-bearing bones like the hips and spine. That's roughly 10 times faster than postmenopausal osteoporosis, one of the most aggressive forms of bone loss on Earth. Muscle mass declines as well, particularly in the legs and back, at rates of up to 20% over 6 months. Cardiovascular deconditioning occurs, where the heart, no longer working against gravity to pump blood, becomes less efficient. Vision changes, collectively known as spaceflight-associated neuroocular syndrome, affect more than half of astronauts on long missions, caused by fluid shifting toward the head and increasing pressure on the optic nerve. A 2021 review published in MPJ Microgravity titled "Update on the Effects of Microgravity on the Musculoskeletal System" details these processes. The lack of mechanical loading in microgravity leads to decreased bone formation and increased bone resorption, the process by which bone tissue is broken down. Osteoblasts, cells that build bone, become less active. Osteoclasts, cells that break down bone, continue working. The result is net bone loss. Similarly, skeletal muscle undergoes atrophy. Muscle fibers shrink. Protein synthesis decreases. Protein degradation increases. The muscles literally waste away. Astronauts on the ISS exercise for about 2 hours per day, using resistance machines and treadmills just to slow this process. Even with rigorous exercise, they still lose bone and muscle. Some of the bone loss is permanent. A 2025 study published in MPJ Microgravity examined 2 astronauts 4 years after returning from long-duration spaceflight. One astronaut fully recovered bone density and microarchitecture. The other showed persistent trabecular bone deficits, the spongy interior structure of bones compensated partially by cortical bone thickening, the dense outer layer. The findings suggest that some astronauts may never fully recover skeletal health after extended missions. Now consider an interstellar journey. If astronauts lose bone and muscle on 6-month missions to the ISS despite extensive exercise, what happens on a decades-long voyage? Even with artificial gravity generated by rotating the spacecraft, which introduces engineering challenges and may not perfectly replicate Earth's gravity, long-term biological degradation is almost certain. Radiation adds another layer, damaging cellular repair mechanisms and accelerating aging. By the time you reach your destination, you may be physically incapable of returning. Your bones may be too brittle to withstand the acceleration forces required for a return journey. Your muscles may be too weak to operate spacecraft controls or perform necessary tasks. Your cardiovascular system may be unable to handle the stresses of re-entry and readaptation to gravity. You become a prisoner of your own biology, stranded not just by physics and cosmology, but by the limitations of your own deteriorating body. And then there's the issue of resources. A return journey requires carrying enough fuel, water, food, air, spare parts, and consumables for the entire round trip. Every kilogram of supplies for the return leg must be accelerated during the outbound journey, multiplying fuel requirements. It's not just doubling the mission, it's exponentially increasing the difficulty. The logistics are staggering. A crew of 6 requires roughly 3 kilograms of food, 4 kilograms of water, and 1 kilogram of oxygen per person per day. Over a 40-year round-trip mission, that's approximately 175,000 kilograms of consumables, assuming perfect recycling, which doesn't exist. In reality, recycling systems on the ISS recover about 90% of water. Losses accumulate. You'd need to carry extra, and food cannot be fully recycled. It must be grown or stored. Growing food in space requires equipment, energy, light, nutrients, and space. Hydroponic or aeroponic systems add mass and complexity. Failures could be catastrophic. A blight could wipe out crops. Equipment malfunctions could halt production. Unlike Earth, where a failed harvest means hardship but not necessarily death, in space it means starvation, water recycling systems, air revitalization systems, waste management, temperature control, radiation shielding. All of these systems must function flawlessly for decades. No resupply missions are coming. No rescue is possible. If a critical system fails and cannot be repaired with onboard resources, the mission ends in tragedy. The spacecraft itself degrades over time. Micrometeorite impacts, radiation damage, thermal cycling, vibration from onboard machinery all take their toll. Metal fatigues, seals crack, electronics fail, software becomes outdated, the ship becomes a gradually decaying artifact, holding its fragile human cargo in an increasingly precarious shell. And we haven't even discussed communication delays. At relativistic speeds, time dilation affects communication in strange ways. But even at sub-relativistic speeds, the sheer distance introduces delays measured in years. A message sent from a star system 10 light-years away takes 10 years to reach Earth. A reply takes another 10 years to return. By the time you receive guidance from mission control on how to fix a critical system, 20 years have passed. The problem may have killed you a decade ago. This communication delay severs the psychological umbilical cord connecting explorers to home. You cannot consult with experts in real time. You cannot share your experiences with loved ones in any meaningful interactive way. You send messages into the void, knowing that by the time a response arrives, if it arrives, you may be dead. Circumstances may have changed beyond recognition, or the message may no longer be relevant. Imagine sending a message to Earth saying, "We've arrived safely. The planet looks habitable. We're beginning exploration." That message takes 10 years to arrive. Earth celebrates. They send congratulations and instructions. 10 years later, you receive their message. But in those 20 years, the situation has changed. Maybe the planet wasn't habitable after all. Maybe conflict erupted among the crew. Maybe everyone is dead. Earth doesn't know. They won't know for another 10 years when the next message fails to arrive, or arrives containing tragic news. This temporal disconnection creates a kind of existential loneliness, unlike anything experienced in human history. Explorers of Earth's past, no matter how remote their destinations, remained connected to their cultures through the continuity of time. Even if they died in distant lands, they lived in the same era as their homelands. But interstellar travelers become unstuck in time, living in a present that is increasingly divorced from Earth's present, receiving messages from a past that no longer exists, sending messages to a future they will never see. And then there's the question of purpose. Why return? If you've reached another star system, established a presence there, perhaps even found life or habitable worlds, what draws you back to Earth? By the time you could return, everyone you knew is dead. Your culture has evolved beyond recognition. The political and social structures that sent you no longer exist. You would be arriving not as a returning hero, but as an anachronism, a relic from a bygone age bearing news that is decades or centuries out of date. Some might argue that the knowledge you bring back justifies the return. Scientific data, information about other worlds, confirmation of life beyond Earth. But in the age of digital communication, why physically return? Send the data via radio waves or laser transmissions. It travels at light speed, far faster than any spacecraft could. Yes, bandwidth is limited and transmission times are long, but over years or decades, you could transmit vast amounts of information. The physical return of the crew adds little scientific value while multiplying risk and cost enormously. Others might argue for the symbolic importance of return. The hero's journey, the completion of the circle, the human need for closure. These are valid psychological motivations, but they must be weighed against the practical impossibilities we've discussed. The universe doesn't care about our narratives. Physics doesn't bend to our psychological needs. There's also the sobering reality that interstellar colonization, if it happens, will likely be a one-way endeavor. Those who leave will be founders of new branches of humanity, forever separated from Earth. They will carry with them the DNA, culture, knowledge, and technology of Earth, but they will evolve independently, shaped by different environments, different selection pressures, different histories. Within a few generations, the colonists' descendants will have no personal connection to Earth. It will be a mythical place, the ancestral homeland, revered perhaps, but not home. Their home will be the new world. Their identity will be shaped by that world's unique conditions. They will become, in effect, a new subspecies of humanity, possibly even a new species entirely, if isolated long enough and subjected to different evolutionary pressures. This is not necessarily tragic. It's the continuation of a pattern that has played out throughout the history of life on Earth. Species branch, populations separate, evolution proceeds along different paths. Humanity has always been a wandering species. Our ancestors left Africa, spread across the globe, adapted to diverse environments, developed distinct cultures, and to a small degree, distinct physical traits. Interstellar colonization would simply extend this pattern to a cosmic scale, but it does mean that the notion of return becomes increasingly meaningless over generational timescales. The ship that left Earth carries people with memories of Earth, connections to Earth, reasons to return. But the second generation, born in transit, knows Earth only through stories and recordings. The third generation knows it even less. By the 10th generation, Earth is ancient history, as remote and abstract to them as the savannas of Africa are to modern city dwellers. Some missions might employ generation ships, massive vessels designed to house multiple generations during the journey. These ships would be self-contained worlds, miniature ecosystems supporting human life for centuries. The people who arrive at the destination would be the distant descendants of those who departed. They would have lived their entire lives in transit, knowing nothing but the interior of the ship. The psychological and sociological challenges of generation ships are staggering. How do you maintain social cohesion over centuries? How do you prevent cultural stagnation or fragmentation? How do you ensure that the 100th generation remains committed to a mission their ancestors began? What if they decide they don't want to continue? What if they want to turn back, or stop, or alter the destination? Who has the authority to decide? There's also the question of genetic diversity. A small founding population, even a few hundred individuals, carries limited genetic variation. Over generations, inbreeding becomes inevitable unless carefully managed through genetic engineering or artificial reproductive technologies. Without intervention, the population could suffer from inbreeding depression, an accumulation of harmful recessive alleles that reduce fitness, increase disease susceptibility, and lower fertility. Studies of isolated human populations on Earth, such as island communities, demonstrate these effects. Founder effects, genetic bottlenecks, and drift can lead to increased prevalence of genetic disorders. On a generation ship, without access to a larger gene pool, these problems could become catastrophic. The mission could fail not because of technology, but because of biology. Genetic engineering could mitigate this, introducing variation artificially, editing embryos to eliminate harmful mutations, diversifying immune system genes to maintain disease resistance. But this introduces ethical dilemmas. Who decides which traits to preserve or enhance? What constitutes a harmful mutation? Where is the line between correcting disorders and engaging in eugenics? These are not abstract philosophical questions. They have real consequences for the people living aboard generation ships, and they compound the impossibility of return. Even if a generation ship could physically turn around, which would require carrying enough fuel for deceleration, turnaround, and re-acceleration, a staggering amount, the people aboard would have no meaningful connection to the Earth they're returning to. They would be aliens visiting a foreign world, even though that world is humanity's cradle. If you are enjoying this journey, make sure to subscribe to the channel. You'll be joining a community of curious minds exploring the greatest questions humanity has ever asked. Let's also consider the sheer scale of interstellar distances in more tangible terms. The nearest star system, Alpha Centauri, is about 4.4 light-years away, roughly 41 trillion kilometers. If you could travel at 1% the speed of light, a velocity far beyond our current capabilities, the journey would take 440 years one way. At 10% light speed, which would require staggering amounts of energy and expose you to intense radiation from the interstellar medium, it would still take 44 years. Most proposed interstellar missions target higher speeds to reduce travel time within a human lifetime. The Breakthrough Starshot initiative, a real project backed by significant funding, aims to send tiny light sail probes to Alpha Centauri at 20% the speed of light. Even at that incredible velocity, the journey takes about 20 years. But here's the critical point. Breakthrough Starshot is not designed for a return journey. The probes are one-way. They'll send data back via laser, but they will never return. Scaling this up to a crewed mission multiplies every challenge. A human-carrying spacecraft is vastly more massive than a tiny probe. It requires life support, radiation shielding, power generation, propulsion systems capable of acceleration and deceleration, living space, supplies. The energy requirements become astronomical, literally. Accelerating even a modest spacecraft to 20% light speed would require energy equivalent to a significant fraction of humanity's total annual energy consumption. And then you have to slow down at the destination, which requires the same amount of energy again. If you want to return, you need to accelerate back toward Earth and then decelerate upon arrival. 4 massive energy expenditures. The fuel for these maneuvers must be carried from the start or harvested at the destination, which assumes resources are available and accessible, a huge uncertainty. Antimatter has been proposed as a fuel source because of its unparalleled energy density. When matter and antimatter annihilate, they convert mass directly to energy according to Einstein's equation, E = mc². Even tiny amounts of antimatter release enormous energy, but antimatter doesn't exist naturally in usable quantities. It must be manufactured in particle accelerators, 1 atom at a time, at enormous cost. Current production rates are measured in nanograms per year. Spacecraft would need kilograms, possibly tons, even if we could produce sufficient antimatter. Storing it is incredibly dangerous. Antimatter annihilates instantly upon contact with normal matter, releasing energy. Containment requires magnetic or electric fields to suspend the antimatter in a perfect vacuum, never touching the container walls. Any failure results in catastrophic explosion. The engineering challenges are immense, and we're nowhere near solving them. Fusion propulsion, where hydrogen nuclei fuse to form helium, releasing energy, is another possibility. Fusion powers the stars, and humanity has achieved fusion reactions in laboratories and hydrogen bombs, but controlled, sustained fusion for propulsion remains elusive. Decades of research have yet to produce a fusion reactor that outputs more energy than it consumes. Fusion propulsion for spacecraft is even more distant. There are more exotic ideas. Bussard ramjets, which scoop up interstellar hydrogen and fuse it for propulsion. Warp drives, which manipulate space-time itself to achieve faster-than-light travel without violating relativity. Wormholes, hypothetical tunnels through space-time connecting distant points. But all of these remain firmly in the realm of theoretical physics. None have been demonstrated, and most require materials or energy densities that may not exist in our universe, such as exotic matter with negative energy density. Even if one of these speculative technologies proves feasible, the timescale for development is uncertain. It could be decades, centuries, or never. Planning a return journey based on technologies that don't yet exist is wishful thinking, not mission planning, so we're left with the technologies we understand. Chemical rockets, ion drives, maybe fusion if we're optimistic, and light sails pushed by powerful lasers. All of these enable one-way missions at best. Return journeys remain beyond reach, and beyond the propulsion challenges, there's another silent killer waiting in the vast emptiness between stars: radiation. Space is awash with radiation. Galactic cosmic rays, high-energy particles accelerated by supernova explosions and other violent cosmic events, permeate the galaxy. Solar particle events, bursts of energetic protons and other particles from the Sun, pose additional hazards within our solar system. In interstellar space, far from any star's protective magnetosphere, cosmic radiation becomes the dominant threat. Galactic cosmic rays consist primarily of protons, but also include heavier ions like helium, carbon, and iron nuclei, traveling at significant fractions of the speed of light. These high-energy, high-charge particles, collectively called HCE particles, are particularly dangerous. When an HCE particle passes through living tissue, it deposits energy along its path, damaging DNA, proteins, and cellular structures. Unlike the relatively low-energy X-rays or gamma rays used in medical imaging, HCE particles create dense tracts of ionization, causing clustered DNA damage that is difficult for cells to repair. The biological effects are severe. Increased cancer risk is the most well-known consequence. A 2023 study published in the International Journal of Molecular Sciences estimated radiation doses for a hypothetical Mars mission, accounting for galactic cosmic rays under different shielding scenarios. The researchers found that for a 650-day mission during solar minimum, when cosmic ray intensity is highest, astronauts would receive effective doses approaching or exceeding 1 sievert, the career dose limit recommended by the International Commission on Radiological Protection. But interstellar missions last far longer than Mars missions, decades, possibly centuries. Even with shielding, the cumulative radiation dose would be enormous. Thick shielding can block some radiation, but it adds mass which multiplies fuel requirements, and certain types of radiation, particularly high-energy HCE particles, penetrate deeply. Some shielding materials even produce secondary radiation when struck by cosmic rays, creating a cascade of particles that can be more dangerous than the original radiation. A 2026 review published in the European Physical Journal Plus, titled Radiation Risk Mitigation in Human Space Exploration, emphasizes that space radiation remains one of the major showstoppers for deep space exploration. The paper calls for better understanding of space weather, more accurate dosimetric instruments, improved risk models, and effective countermeasures. But as of now, no perfect solution exists. Astronauts on interstellar missions will accumulate radiation exposure far exceeding any safe limit defined by terrestrial standards. The health consequences extend beyond cancer. Radiation damages the central nervous system, potentially causing cognitive decline, memory impairment, and behavioral changes. Studies on mice exposed to simulated cosmic rays show persistent deficits in learning and memory, increased anxiety, and altered social behavior. A 2024 review published in Frontiers in Physiologies discusses how long-term space radiation exposure affects nearly every organ system: cardiovascular disease, cataracts, immune system dysfunction, accelerated aging. Imagine traveling for 20, 30, 40 years through interstellar space, your body bombarded constantly by cosmic rays, your cancer risk climbs, your brain function deteriorates, your organs age prematurely. Even if you survive the journey, you may arrive at your destination with diminished cognitive capacity, chronic health problems, and a shortened lifespan. Returning to Earth, if it were physically possible, would subject you to another decades-long radiation bath, compounding the damage. And radiation isn't the only hazard lurking in the interstellar medium. Dust is everywhere. The space between stars is not a perfect vacuum. It contains gas, primarily hydrogen and helium, and dust grains, tiny solid particles composed of silicates, carbon, and ice. The density is extremely low, about 1 hydrogen atom per cubic centimeter on average, with dust densities even lower. But at relativistic speeds, even these sparse particles become deadly projectiles. Consider a spacecraft traveling at 20% the speed of light, as proposed by breakthrough Starshot. At this velocity, a collision with a dust grain the size of a bacterium, massing perhaps a trillionth of a gram, releases energy equivalent to a stick of dynamite. The grain vaporizes on impact, creating a plasma fireball with temperatures exceeding 10 million Kelvin. This plasma explodes outward, gouging craters, melting material, and sending shockwaves through the spacecraft structure. A 2018 study published in the Journal of the British Interplanetary Society, authored by researchers at Lawrence Livermore National Laboratory, used computer simulations to model dust grain impacts on relativistic spacecraft. They found that the grain's energy is deposited in a long, thin cylindrical volume, creating extreme temperatures and pressures. The resulting damage depends on the spacecraft material and geometry, but can include melting, vaporization, crater formation, and structural failure. For thin structures like light sails, grains punch straight through, leaving small holes. If the holes are numerous enough, the sail's integrity degrades, reducing propulsion efficiency. For thicker structures, like crew habitats, all the grain's energy deposits internally, potentially causing catastrophic damage. The researchers explored shielding strategies, placing a thin sacrificial shield in front of the main spacecraft to atomize incoming grains and disperse their energy before they reach critical systems. But this adds mass and complexity. A 2017 paper published in the Astrophysical Journal by researchers including Harvard's Abraham Loeb examined the interaction of relativistic spacecraft with the interstellar medium in detail. They calculated that dust bombardment would erode the spacecraft surface by approximately 0.5 millimeter after traversing a column density typical of the path to Alpha Centauri. Gas bombardment, primarily hydrogen and helium nuclei, damages the surface through a process called sputtering, where incoming ions knock atoms off the surface, and through radiation damage to the material's crystal structure. For materials like quartz, gas bombardment can damage the surface to depths of about 1/10 of a millimeter. Graphite and other carbon-based materials fare better due to their lower atomic number and higher resistance to radiation damage. But over decades of travel, the cumulative effects degrade shielding, sensors, optical systems, and structural components. The spacecraft literally erodes away as it flies. These findings are based on small, gram-scale probes like those envisioned by breakthrough Starshot. Scaling up to crewed spacecraft, which must be thousands or millions of times more massive, introduces further complications. More surface area means more impacts. Critical systems like windows, sensors, radiators, and communication arrays are vulnerable. Redundancy helps but adds mass. Repairing damage in flight is possible in principle, but requires carrying spare parts, tools, and trained personnel, all of which add mass and complexity. The interstellar medium also varies in density. Denser regions like molecular clouds contain more gas and dust, increasing collision rates. Navigating around these regions is possible if you can detect them in advance and adjust course, but course corrections require fuel, and predicting the interstellar environment decades in advance, across light years of distance, is extraordinarily difficult. You're essentially flying blind, hoping the path ahead is clear. There's also the issue of navigation itself. Stars move. Over the years or decades of an interstellar journey, Your target star system moves relative to the Sun. The motion is small, but over interstellar distances, small errors compound. You must continuously update your trajectory based on observations, which requires functional sensors and propulsion systems capable of making mid-course corrections. If your sensors are damaged by dust impacts or radiation, or if your propulsion system fails, you could miss your target entirely, drifting past into the infinite void. And let's not forget the psychological dimension of this navigation challenge. Imagine being responsible for piloting a spacecraft carrying dozens or hundreds of people across light years of space, knowing that a single miscalculation could doom everyone aboard. The pressure would be immense, and if something goes wrong, there's no mission control to consult in real time, no rescue mission coming to save you. You're on your own, millions or billions of kilometers from the nearest help. The isolation, the danger, the responsibility, all of it compounds the psychological stresses we discussed earlier. Studies of Antarctic winter overcrews who spend months in isolation but at least know they're on Earth and can be evacuated in emergencies show significant mental health challenges. Interstellar travelers face isolation on a scale unprecedented in human experience, with no possibility of evacuation, no end in sight except arrival at a distant destination or death. And here's another grim reality. The possibility of mission failure increases with mission duration. Every system aboard the spacecraft has a failure rate. Electronics fail due to radiation-induced bit flips, where cosmic rays alter data in computer memory. Mechanical systems wear out, seals degrade, software develops bugs or becomes incompatible with aging hardware. The longer the mission, the higher the cumulative probability that something critical will fail catastrophically. Reliability engineering teaches us that complex systems fail in predictable ways. The probability of system failure over time follows exponential decay curves. For a mission lasting a few months, like Apollo lunar missions, you can design systems with sufficient redundancy to achieve acceptable failure probabilities, perhaps 1 in 100 or 1 in 1,000. But for missions lasting decades, the mathematics becomes unforgiving. Let's say each critical system has a 99% probability of functioning correctly over 1 year. That sounds good, but over 40 years, the probability that the system never fails is 0.99 to the power of 40, which equals approximately 60%. That means a 33% chance of failure. And a spacecraft has dozens of critical systems: life support, power generation, propulsion, navigation, communication, thermal control, radiation shielding, structural integrity. If anyone fails catastrophically, the mission may be doomed. You can add redundancy, backup systems for every critical component, but redundancy adds mass, complexity, and new failure modes. Backup systems can fail too. And the more complex the system, the more difficult it is to diagnose and repair problems. Astronauts would need to be trained not just as pilots and scientists, but as expert technicians capable of repairing any system aboard. Using only the tools and materials available on board, there's also the problem of spare parts. You cannot carry spares for every possible component. The mass would be prohibitive, so you must predict which parts are most likely to fail and carry spares for those. But predictions are based on statistical models derived from Earth-based testing, which may not accurately reflect the space environment. A component that never fails on Earth might fail routinely in space due to radiation, thermal cycling, vibration, or other factors not captured in the models. Three-dimensional printing offers some hope. If you can carry raw materials and a versatile fabrication system, you can manufacture replacement parts as needed. But this assumes the fabrication system itself doesn't fail, and that you have the raw materials, energy, and expertise to produce complex components in a zero-gravity, radiation-heavy environment. It's promising technology, but not a panacea. And then there's the human element. People make mistakes. Fatigue, stress, boredom, depression, interpersonal conflict. All of these degrade performance and increase error rates. Studies of human error in aviation and other high-stakes environments show that even highly trained professionals make critical mistakes under stress or when tired. On Earth, mistakes can often be corrected. In space, mistakes can be fatal. The Mars 500 simulation I mentioned earlier documented conflicts, sleep disturbances, and cognitive deficits among the crew. And that was a simulation where participants knew they could leave if necessary, where their families were nearby, where Earth's familiar environment was just outside the door. Real interstellar missions would face far greater psychological stresses for far longer durations, with no possibility of escape. Now let's think about governance and decision-making during such a mission. Who's in charge? On short missions like Apollo or Space Shuttle flights, mission control on Earth retains ultimate authority, with the spacecraft commander executing orders and making tactical decisions. But communication delays make this model unworkable for interstellar missions. By the time Earth receives a distress call and sends instructions, years may have passed. The crew must be autonomous, making life or death decisions without guidance from home. But autonomy introduces new challenges. What if the crew disagrees on a critical decision? What if a crew member becomes mentally unstable or dangerous? What if there's a mutiny? On Earth, we have legal systems, law enforcement, judicial processes to resolve disputes and punish wrongdoing. On a spacecraft, these institutions don't exist. The crew must govern themselves, resolve conflicts internally, and enforce discipline without external support. History offers cautionary tales. The mutiny on the HMS Bounty, the fragmentation of isolated Antarctic expeditions, the breakdown of order in disaster scenarios, all demonstrate that humans, under sufficient stress and isolation, can descend into conflict and chaos. Interstellar missions would need robust governance structures, conflict resolution mechanisms, and perhaps even legal frameworks for dealing with crimes or disputes. But designing such systems for small, isolated populations is extraordinarily difficult. There's also the question of reproduction and family. If the mission lasts decades, crew members may wish to form relationships, have children. Do you allow this? Children require resources, space, education, and medical care, all of which strain the mission's capacity. But forbidding reproduction raises ethical issues and could harm morale. Some generation ship concepts assume reproduction is essential, that children born aboard will continue the mission after their parents die. But this creates a society where some members never consented to participate, born into a life they didn't choose, on a journey they can't escape. What rights do these children have? Can they refuse to participate in the mission? Can they demand to return to Earth, even though that's physically impossible? These are profound ethical questions without clear answers, and they illustrate a deeper truth. Interstellar missions are not just technological challenges, they're social and ethical challenges of the highest order. Let's also consider the economics. Interstellar missions would be staggeringly expensive. Developing the technology, building the spacecraft, launching it, supporting the crew, maintaining communication, all of this would require resources on a scale comparable to national GDP. Some estimates for a crewed interstellar mission run into the trillions of dollars, possibly tens of trillions. Who pays for this? Governments, private companies, international consortia, and what's the return on investment? Unlike Apollo, which had geopolitical motivations and delivered prestige and technological spin-offs, interstellar missions offer no clear near-term benefits to the societies funding them. Scientific knowledge, certainly, but knowledge that won't arrive until decades after the mission launches. long after the politicians, CEOs, and taxpayers who funded it are dead. This temporal disconnect between investment and return makes interstellar missions politically and economically difficult to justify. You're asking today's generation to sacrifice resources for benefits their grandchildren or great-grandchildren might enjoy if the mission succeeds, which is far from certain. History suggests that societies struggle to make such long-term commitments. Even century-spanning projects like cathedrals, built over multiple generations, served immediate religious and social purposes for the communities building them. Interstellar missions offer no such immediate gratification. Some argue that the survival of humanity justifies interstellar colonization. If Earth faces existential risks, asteroid impacts, supervolcano eruptions, nuclear war, climate catastrophe, pandemics, artificial intelligence gone rogue, then spreading humanity to other star systems ensures that some branch of our species survives, even if Earth is destroyed. This is the eggs in multiple baskets argument, and it has merit, but the timeline doesn't work. Developing interstellar capabilities will take centuries at minimum, possibly millennia. Meanwhile, existential risks are growing more acute on timescales of decades to centuries. If we're worried about near-term existential threats, we'd be better served investing in planetary defense against asteroids, biosecurity to prevent pandemics, robust climate adaptation, and governance systems to prevent nuclear war. These interventions are far cheaper and more effective than interstellar colonization for reducing near-term risk. In the very long term, yes, spreading beyond Earth becomes essential. The Sun will eventually become a red giant and destroy Earth in about 5 billion years. But 5 billion years is an incomprehensibly long timescale. Humanity in our current form has existed for only about 300,000 years. Civilization has existed for about 10,000 years. Industrial civilization for about 250 years. Projecting our needs 5 billion years into the future is absurd. We have no idea what humanity, if it still exists, will be like. We may be unrecognizable, transformed by genetic engineering, cybernetic enhancement, or digital uploading. We may have transcended biology entirely, or we may be extinct, replaced by our artificial successors. The point is, using the Sun's eventual death as justification for interstellar missions today is intellectually dishonest. It's conflating timescales and ignoring more immediate priorities. If we're serious about long-term survival, we should focus on stabilizing our civilization, developing sustainable technologies, preserving Earth's biosphere, and ensuring we don't destroy ourselves in the next few centuries. If we succeed at that, then, centuries or millennia from now, our descendants can consider interstellar expansion if they deem it worthwhile. But we've wandered from the original question. Why can't you return from an interstellar journey? Let me bring us back to that core issue by considering a specific scenario. Suppose, through some extraordinary breakthrough, we develop a propulsion system capable of accelerating a crewed spacecraft to 10% the speed of light. That's still far beyond our current capabilities, but let's grant it for the sake of argument. You embark on a mission to Proxima Centauri, 4.2 light-years away. At 10% light speed, the journey takes 42 years outbound. You spend, let's say, 5 years exploring the Proxima system. You study the planets, search for life, gather data, then you decide to return. Another 42 years for the return journey. Total mission time, 89 years. Even if you were 25 when you departed, you'd be 114 upon return, assuming you survive. Most likely you'd die before completing the journey, either from old age, radiation exposure, equipment failure, or any number of other hazards. But let's say you survive through some combination of luck, medical technology, and genetic engineering that extends lifespan. You return to Earth after 89 years. What do you find? Everyone you knew is dead. Your family, friends, colleagues, all gone. The world has changed profoundly. Technologies have advanced. Political systems have shifted. Cultural norms have evolved. Languages may have changed. You are a stranger in a strange land, a relic from a bygone era. The astronaut Scott Kelly spent nearly a year on the International Space Station, the longest continuous spaceflight by an American at the time. Upon returning, he described the experience of readaptation as profoundly disorienting. Gravity felt oppressive. His body ached. He struggled with balance and coordination, and that was after less than a year in space. With constant communication with Earth, knowing he was coming home, now imagine returning after nearly a century. The psychological shock would be immense. You might suffer from what we could call temporal displacement disorder, a form of culture shock combined with profound grief for the lost world you left behind. Some returning travelers might develop severe depression, PTSD, or other mental health crises. And Earth's society, having moved on, might view you as a curiosity, a museum piece, not as a person with agency and contemporary relevance. There's also a real possibility that Earth's society upon your return would be hostile or indifferent to you. Resources are finite. A society nearly a century removed from your departure may have no interest in supporting elderly travelers from a bygone era. You might be studied, interviewed, your experiences documented, but then what? Where do you fit in this new world? What role do you serve? You possess knowledge and skills from a civilization that no longer exists, expertise in technologies that have been superseded, cultural references no one understands. Science fiction often depicts returning space travelers as heroes celebrated and honored, but reality is rarely so kind. History shows that explorers returning from distant lands often faced indifference, poverty, or obscurity. Ferdinand Magellan's crew, the first to circumnavigate Earth, returned to Spain after 3 years to find their patron dead, and their achievement barely acknowledged. Many explorers died in poverty. Others were forgotten entirely, and those journeys lasted years, not decades, and the world they returned to was recognizably the same. Now amplify that by orders of magnitude. Your return after a century in space might be met with curiosity, but also with the practical realization that you are economically and socially obsolete. The mission cost trillions. It's done. The data has been transmitted. You, the physical travelers, are expensive to retrieve, expensive to support, and offer little additional value. It's a harsh calculation, but societies make harsh calculations when resources are limited. This brings us to another critical point. The incentive structure for return missions is fundamentally broken. From Earth's perspective, the scientific return on investment comes from the data transmitted, not from the physical return of the crew. Every bit of information discovered can be sent via radio or laser communication. Yes, there's a delay, years potentially, but the information arrives far faster than any spacecraft could return. And once transmitted, the data can be analyzed, replicated, and distributed globally. The physical samples, rocks, soil, atmospheric readings, even biological specimens, if life is found, can be described in enormous detail via transmitted data, three-dimensional scanning, spectroscopic analysis, genetic sequencing if applicable, all can be encoded and transmitted. The value of physically returning a rock from another star system is largely symbolic, not scientific. We can learn almost everything from the transmitted data. So from Earth's perspective, funding a return journey offers marginal scientific benefit at extraordinary cost. The fuel, life support, time and risk involved in bringing the crew home could instead be invested in new missions, new discoveries, new frontiers. It's a cold calculus, but it's the reality of resource allocation in large-scale projects. From the crew's perspective, the incentive to return is personal, not scientific. They want to see Earth again, reunite with humanity, share their experiences directly. But as we've discussed, The Earth they return to is not the Earth they left. The people they knew are gone. The connections that made Earth home have severed. What they're really seeking is closure, a sense of completion, the psychological satisfaction of finishing the journey. But that satisfaction may be outweighed by the trauma of displacement, the grief of loss, the alienation of being temporarily out of sync with their species. Some crew members might choose not to return, even if it were physically possible. Having spent decades traveling to another star system, having invested their entire adult lives in the mission, they might feel more connected to the new world they've discovered than to the old world they left behind. They might choose to stay, to colonize, to build something new, rather than return to a place that is no longer home. This creates a fascinating inversion of the original question. It's not just can you return, but would you want to? And for many, the answer might be no. The psychological and social costs of return might exceed the benefits, making it a choice to reject rather than a goal to pursue. But let's set aside psychology and sociology for a moment and return to the hard physics of why return journeys are so difficult. We've discussed fuel, time dilation, radiation, and navigation. But there's another factor: deceleration at Earth upon return. If you've spent 40+ years accelerating, coasting, and decelerating to reach your destination, you must repeat the process in reverse to return. But here's the problem: Earth is moving. Our planet orbits the Sun at about 30 kilometers per second. The Sun orbits the galactic center at about 220 kilometers per second. The galaxy itself is moving relative to the cosmic microwave background. All of these motions compound, and over decades of travel, they add up. When you left Earth, you matched Earth's velocity, then accelerated away. But by the time you return decades later, Earth has moved. You must not only decelerate from your interstellar velocity, but also match Earth's velocity precisely to achieve orbit or landing. This requires extraordinarily precise navigation and propulsion control. Small errors result in missing Earth entirely, flying past it at relativistic speeds, unable to turn around. Imagine you're decelerating as you approach the solar system after a 40-year return journey. You're still traveling at a significant fraction of light speed, let's say 5%, about 15,000 kilometers per second. At this velocity, you cross the distance from the Sun to Earth, about 150 million kilometers, in less than 3 hours. If your navigation is off by even a tiny fraction, you miss Earth, and at these speeds, you cannot simply turn around and come back. The fuel required for such a maneuver is prohibitive, so you get one shot, one chance to decelerate at exactly the right time with exactly the right trajectory, to intersect Earth's orbit at exactly the moment Earth is there. The precision required is extraordinary, far exceeding anything we've attempted. And remember, you're doing this after decades in space, with aging equipment, degraded sensors, and a crew that may be physically and mentally compromised by the journey. Space agencies on Earth could assist by transmitting navigation updates, providing real-time data on Earth's position and velocity. But the communication delay means you're working with information that is years out of date by the time you receive it. You must extrapolate forward, predicting where Earth will be when you arrive, based on incomplete information. The margin for error is razor thin, and if something goes wrong, if you miss Earth, there's no second chance. You fly past, out into the outer solar system, your velocity too high to return. You could potentially decelerate further, using your remaining fuel, and attempt to reach one of the outer planets, establish orbit there, and signal for rescue. But who's coming to rescue you? Building and launching a rescue mission takes years, and by the time it reaches you, you may be dead, your life support exhausted, your systems failed. The rescue mission itself faces all the same challenges we've discussed: propulsion, life support, navigation, cost. Rescuing a stranded interstellar crew in the outer solar system would be one of the most difficult and expensive operations ever attempted. It might not be politically or economically feasible. You could be left to die, your fate a tragic footnote in the history of space exploration. This is the brutal reality of interstellar travel. There are no safety nets, no emergency services, no Coast Guard coming to tow you to shore. You are utterly dependent on your own systems, your own expertise, your own luck. And the farther you travel, the more tenuous that dependence becomes. Let's also talk about the destination itself. We've been assuming that the target star system is hospitable or at least interesting enough to justify the mission. But what if it's not? What if you travel for decades to reach Proxima Centauri, only to find that Proxima b, the potentially habitable planet, is actually a lifeless radiation-scorched rock, tidally locked to its star, with one side perpetually burning and the other frozen? Recent observations suggest Proxima b receives intense stellar radiation and particle bombardment from Proxima Centauri, a red dwarf star prone to violent flares. The planet may have lost its atmosphere entirely, sterilized by radiation. Even if it retains as an atmosphere, conditions might be completely inhospitable to life as we know it, and potentially even to human habitation with technology. You arrive after decades of travel, expecting to find a new world to explore, perhaps even to settle. Instead, you find disappointment. The mission's primary objective, finding a habitable world or signs of life, is unfulfilled. Decades of effort, trillions in investment, enormous human cost, all for nothing. What do? You could explore the system thoroughly, catalogue the planets, moons, asteroids, gather as much data as possible. This salvages some scientific value from the mission. But the emotional and psychological impact on the crew would be devastating. They've sacrificed their entire lives for this mission, endured unimaginable hardship, and the payoff is a barren system, offering nothing but scientific trivia. Do you attempt to return to Earth, facing all the challenges we've discussed, knowing you're returning in failure? Or do you push on to another star system, hoping the next one is better, extending your journey by additional decades, increasing the risks, depleting your remaining resources? Or do you settle in the disappointing system anyway, making the best of a bad situation, establishing a colony on a marginal world because going home is impossible and continuing on is too risky? These are agonizing decisions with no good options, and they illustrate why interstellar exploration is so different from terrestrial exploration. On Earth, if an expedition reaches a destination and finds it uninteresting, they simply return home, disappointed but alive, ready to try again elsewhere. In interstellar space, return is not a simple option. You're committed, for better or worse, to living with the consequences of your destination's reality. There's also the problem of obsolescence. Technology advances exponentially. The spacecraft you launch today will be obsolete by the time it reaches its destination decades hence. A faster ship launched years after yours could overtake you mid-journey, reaching the destination first, making your mission redundant. This is sometimes called the weight calculation. If technology improves at a predictable rate, there's always a later time when a faster, better mission could be launched that would arrive sooner than a mission launched today. Therefore, you should wait until technology improves. But this logic leads to infinite delay. There's always a reason to wait for better technology. The resolution is to launch when the expected improvement rate slows enough that waiting no longer offers significant advantage. But for interstellar missions, we're nowhere near that point. Our propulsion technology is still primitive. Improvements could be dramatic. A ship launched in 2070, for example, might have propulsion systems 10 times more efficient than anything available in 2030, allowing it to overtake the earlier mission and arrive decades sooner. Imagine being on that first ship, launched in 2030, crawling through space at a fraction of light speed, knowing that newer, faster ships are being built back on Earth. Decades into your journey, you receive a transmission. A new mission launched 5 years ago. They'll reach Proxima Centauri in 15 years. You still have 30 years to go. Your mission is now redundant. We're sorry. What do? Continue anyway. Knowing you'll arrive to find a colony already established, your discoveries already made, your sacrifice rendered meaningless. Abort and attempt to return, if that's even possible. Divert to a different, more distant target, extending your journey even further into the unknown. Each option is bleak, and this scenario is not far-fetched. It's a predictable consequence of launching interstellar missions before propulsion technology matures. This creates a perverse incentive. No one wants to be on the first mission because it's almost certain to be obsolete before arrival. Better to wait for later missions with better technology. But if everyone thinks this way, no mission ever launches. It's a collective action problem, a coordination failure that could stall interstellar exploration indefinitely. Some theorists propose solving this with generation ships designed to be upgraded mid-flight. As new technologies are developed on Earth, the information is transmitted to the ship, and the crew fabricates and installs the upgrades using onboard manufacturing. In principle, this allows the ship to continuously improve, keeping pace with Earth's technological progress, but this assumes several things: that new technologies can be transmitted as information and manufactured from available materials aboard the ship, that the crew has the expertise to install complex new systems while traveling through space, and that upgrades are compatible with the existing ship architecture. In practice, these assumptions are questionable. Many technologies require specialized materials or manufacturing processes that can't be replicated aboard a spacecraft. Installing major upgrades mid-flight might require extensive disassembly and reconstruction, risking catastrophic failure. And there's the issue of information transmission. Sending detailed technical specifications for a new propulsion system or life support upgrade requires enormous data transmission over interstellar distances. The bandwidth is limited, the error rates are high. Compressing decades of engineering development into transmittable data packets is a monumental challenge. And even if you succeed, there's no guarantee the ship's crew can successfully implement the upgrades. We're left with a sobering conclusion. Interstellar missions, once launched, are essentially frozen in time, technologically speaking. The ship that leaves Earth is, with minor modifications, the ship that arrives at the destination. If that ship is based on 21st century technology, it remains a 21st century ship, even if it arrives in the 22nd or 23rd century, surrounded by a galaxy where technology has advanced far beyond it. This technological fossilization extends to the crew as well. The knowledge, skills, and cultural norms they carry reflect the era of their departure, not the era of their arrival. They become time travelers, not through relativistic effects, but through simple isolation. And if they return as anachronisms, people out of their time, struggling to adapt to a world that has moved on without them. Now let's consider one more barrier to return: the psychological transformation of the travelers themselves. Decades in space, isolated from Earth, surrounded by the same small group of people, facing constant danger and hardship, fundamentally changes you. Psychology research on extreme environments, from Antarctic stations to submarines, shows that prolonged isolation and confinement alter personality, cognition, and social behavior in profound ways. People become more introverted, less emotionally expressive, more rigid in their thinking. They develop strong in-group bonds with their companions, but become suspicious or hostile toward outsiders. Their sense of time distorts, days blur together, long-term planning becomes difficult. Some develop what's called long eye, a 1,000-yard stare common among sailors on long voyages, a dissociation from immediate surroundings, a retreat into interior mental space. For interstellar travelers, these effects would be magnified by orders of magnitude. Decades in a confined spacecraft, seeing the same faces every day, eating the same recycled food, breathing the same recycled air, performing the same routines, the monotony would be crushing. Your psychological identity would shift. You'd stop thinking of yourself as a person from Earth and start identifying primarily as a crew member, a traveler, a wanderer. Earth would become an abstraction, a memory, a story you tell yourself, not a place you truly belong. By the time you return, if you return, you might no longer be capable of reintegrating into Earth society. The noise, the crowds, the constant stimulation, the social complexity, it would all be overwhelming, incomprehensible. You'd be psychologically adapted to the sparse, controlled environment of the spacecraft, and Earth would feel alien, chaotic, hostile. This is not speculation. Studies of long-duration submariners and Antarctic winter-over crews show that readaptation to normal society after even 6 to 12 months can take weeks or months, with some individuals experiencing lasting psychological effects. Extrapolate this to decades, and the readaptation period could extend years, possibly a lifetime. Some returning travelers might never fully readapt, remaining psychologically marked by their journey forever. There's also the issue of identity fragmentation. On a multi-decade journey, especially a generation ship where children are born aboard, distinct cultural identities emerge. The crew develops its own language, slang, inside jokes, traditions, rituals. They might develop their own moral codes, different from Earth's norms. Adapted to the unique demands of space travel, they might develop their own governance structures, their own status hierarchies, their own art and music and storytelling traditions. By the time they reach their destination or return to Earth, they are no longer Earthlings visiting another world. They are a distinct cultural group shaped by their unique environment and experiences. Anthropologists call this ethnogenesis, the emergence of a new ethnic or cultural identity, and once such an identity forms, it's remarkably persistent, often lasting generations. The returning travelers, or their descendants, might view themselves as a separate people, distinct from Earth's humanity. They might resist reintegration, preferring to maintain their separate identity. This could lead to conflict, misunderstanding, even violence. Earth's societies might view them as alien, strange, potentially threatening, and the travelers might view Earth's societies as soft, decadent, morally compromised. Having not endured the hardships of space, this cultural divergence creates another barrier to return, a social and psychological barrier as formidable as the physical ones. Even if you physically can return to Earth, you might find that you no longer want to, that you no longer fit, that you've become someone else entirely, someone for whom Earth is no longer home. And let's not forget the biological changes. Decades in space exposed to microgravity, radiation, artificial environments will alter your body in ways we're only beginning to understand. Bone density decreases, muscles atrophy despite exercise, the cardiovascular system adapts to low-gravity conditions, vision changes, immune function is compromised. Astronauts on the International Space Station experience these effects after just 6 months. Over decades, the changes would be profound. Some effects might be irreversible. If you're born and raised in space, on a generation ship, your body develops in microgravity. Your bones grow differently. Your muscles never adapt to Earth's gravity. Your heart and circulatory system are calibrated for low-stress environments. Landing on Earth with its 1G gravity might be physiologically impossible for you. You might literally be unable to stand, unable to support your own weight, unable to pump blood against gravity's pull. Studies on mice born in microgravity showed developmental abnormalities, particularly in the vestibular system responsible for balance and spatial orientation. Human children born in space might face similar challenges. They might be permanently adapted to space, incapable of living on a planetary surface. For them, Earth wouldn't just be psychologically alien, it would be physically uninhabitable. This creates a tragic irony. The very act of traveling to the stars might make it impossible for travelers or their descendants to return home. They become permanently exiled, not by choice but by biology, their bodies transformed by the journey into forms unsuited for the world they left behind. And even if you're an adult when you leave, spending decades in space before returning, the biological toll might be so severe that you require constant medical intervention to survive on Earth. Imagine returning at age 85 after a 60-year mission, your bones brittle, your muscles wasted, your immune system compromised, your cardiovascular system failing. You'd require intensive medical care, possibly for the rest of your life. The cost would be enormous. The quality of life would be poor. You survived the journey, but at what price? Some futurists propose biological or cybernetic enhancement to solve these problems, genetically engineer humans to be radiation resistant, to maintain bone density in microgravity, to require less food and oxygen, augment them with cybernetic implants that regulate physiology, repair damage, enhance cognitive function. In principle, such enhancements could make interstellar travel more feasible and reduce the physical toll. But these solutions introduce new problems. Enhanced or augmented humans might no longer be fully human in the traditional sense. They might be seen as other, as something different, potentially threatening. Returning to Earth after decades in space, heavily modified, you might face discrimination, fear, or outright hostility. Earth's unmodified humans might view you as a freak, a monster, an evolutionary dead end. You might view them as primitive, unenhanced, inferior. This divergence could accelerate the cultural fragmentation we discussed earlier. Enhanced space travelers and unmodified Earth dwellers might diverge so much that they're effectively different species, unable to interbreed, unable to empathize, unable to coexist peacefully. The return from interstellar space might not be a reunion, but a first contact scenario between two branches of humanity that have evolved in different directions. Science fiction explores these themes extensively. In works like Ender's Game, The Forever War, and Aurora, returning space travelers find themselves alienated from Earth, unable to reconnect with a society that has moved on. These stories resonate because they capture a deep truth. Distance in space and time transforms us. The journey changes the traveler, and the greater the journey, the more profound the change. So why can't you return from an interstellar journey? Not because it's physically impossible, though it's extraordinarily difficult, not because Earth won't be there, though it will be profoundly changed, but because you won't be you anymore. The person who left Earth will not be the person who returns. The journey will have transformed you, physically, psychologically, socially, into someone for whom Earth is no longer home, for whom return is not salvation but alienation. This is the deepest and most unsettling answer to your question. Interstellar travel is not just a physical journey across space. It's a one-way transformation of the self. You can perhaps physically return to Earth's coordinates, to the planet where you were born, but you cannot return to the world you left, because that world no longer exists. And more importantly, you cannot return to being the person who left, because that person has been fundamentally altered by the experience of traveling between the stars. If you are still watching, please subscribe to the channel. Here you will stay connected with the latest breakthroughs in astronomy and astrophysics. Perhaps the real lesson is that interstellar journeys are, by their very nature, one-way trips. not because the physics forbids return, but because the nature of the journey makes return meaningless. The destination is not another star system. The destination is transformation itself. You travel not to arrive somewhere else, but to become someone else. And in that sense, there is no return possible, because the person who might return no longer exists. Yet despite all these formidable barriers, I don't want to end on complete pessimism. Human history is filled with challenges that seemed impossible until we solve them. Flight, space travel, nuclear energy, computers, all were dismissed as fantasies until they became reality. Perhaps we will develop breakthrough propulsion technologies we cannot yet imagine. Warp drives that circumvent relativity, wormholes that create shortcuts through space-time, generation ships so well designed that centuries-long journeys become sustainable. Perhaps we'll achieve digital consciousness uploading, transmitting our minds as information at the speed of light, reconstructing ourselves at the destination from local materials, then transmitting ourselves back. Perhaps we'll develop medical technologies that halt aging, repair radiation damage, regenerate tissues, allowing travelers to survive journeys lasting centuries. Perhaps we'll create entirely new forms of governance, psychology, and social organization suited to the unique demands of interstellar migration. And perhaps, most optimistically, we'll develop such profound understanding of ourselves and our place in the cosmos that the question of return becomes irrelevant. Perhaps future humans will embrace the journey itself as the purpose, finding meaning not in arriving or returning, but in the experience of traveling, exploring, discovering, transforming. The stars are calling, as they always have. But answering that call requires accepting that it's a one-way conversation. We can send our descendants to the stars, but they may never truly come home. Now imagine breaking every law we just discussed, 1 light year per second, the universe blurring past you. What would you actually see? Click the video on screen to see what the cosmos looks like at that impossible speed. The first 10 seconds alone will blow your mind.